Okay. Oh, all right. Well, happy Monday. It's we're just moving right along. 102B. Okay. So I think on Friday's lecture, I left off. I said, this is how we can do linear regression in matrix notation. And one of the nice things about working in matrix notation is that you can add more predictor variables, more columns to your X matrix. And the vector-based calculus remains the same. Okay, you don't have to, if you had separate equations and separate partial derivatives, now you have this complicated system of equations that's going to be a pain to solve. But by using matrix notation, we could go from, basically 2 columns in our X matrix to 3 to 4 to 5 to 6 columns in our X matrix. Our matrix notation remains exactly the same. The solution, X transpose X inverse X transpose T or Y or whatever we're calling it, remains the same. And we left off, I said, here's our Olympic data, where we're looking at the gold medal time for the 100-meter dash. And, we see, as the years have gone by, it seems like the winning race time has gotten faster, okay? And we said, well, let's try fitting a few different models. We said, let's fit a linear and a quadratic and a cubic and a fourth order, different order polynomial things. And we can plot it. And this is kind of what it looks like. And really, this graph is pretty because of the different colors, but it's actually not really useful or helpful, because if I asked you to look at this and tell me which color line does the best fit, I don't think we could really, it's kind of like spaghetti over here, and so it's really hard to actually make sense of it. It just looks kind of fun because of the colors. But anyway, this is I think where we left off, and I said, if we take the classical approach, right? I think you guys already all took Stats 101A and you learned linear regression. Maybe you haven't taken it, but you fit your linear model, you run summary, and you get the little stars and the p-values for each thing. You have the AIC and the BIC and the, I don't know, whatever kind of selection method, right? Forward, stepwise, variable selection, or backwards, whatever we're doing, right? And you're supposed to balance kind of this knowledge about the variables. Does it make sense to use this? You balance your knowledge of kind of the statistics and the math. Are my assumptions being violated? And you have to kind of ask, like, what does it mean for there to be a quadratic or a cubic relationship to time? Let's say the third order relationship does actually hold true between the year in which the Olympics were held and the winning race time. And what does that even mean, right? Like, at a certain point, we kind of lose the interpretability, just because I don't know what it means to take the year and cube it. Like in physics, certain things make sense, right? Like you have speed and acceleration and the change in acceleration, which I think we call the jerk. Is that right? I don't remember. It's been a while since physics class. But anyway, you have these things, but sometimes you're just like, oh, okay, there's a cubic relationship with the year in which the Olympics were held. And what does that even mean? A sixth order relationship. I don't know if there's anything in real life that I encounter with a sixth order polynomial relationship. And it's hard to kind of reason about. And at some point you just say, well, it seems to work, and that's it. Okay. So in machine learning, we often remove, for better or worse, the thinking part, okay? And this is, I would say, a very valid criticism of machine learning, but also maybe we justify it by saying, hey, it's making good predictions, so it's okay. Even if we don't understand what's happening, if we like the output, then we're happy, right? It's kind of like, how do you explain the algorithms behind, these apps that, keep feeding you videos? And we don't really know, right? Is it, there's conspiracy theories about, it keeps, the algorithms and the apps are promoting some certain, political agenda by feeding you certain types of videos. And I don't know what's actually going on, but it's hard for me to believe that, because I don't think anybody actually knows what's happening inside the algorithm. All we just know is, hey, you know what? It's promoting videos, and people like the videos that are being promoted, so it's working, and we're happy. And that's kind of what's going on with cross-validation in machine learning. Is it removes a lot of the thinking and the skillful thinking, but sometimes, the flip side is maybe it's just arbitrary decisions, and we just replace it with a validation strategy of just saying, like, hey, if our predictions are good, we're happy. If the output is good, we're happy, even if we don't quite understand, what's going on. And so cross-validation, the way it works is that we take the available data, our observed data, and we split it into two parts. We split it into a training set and a validation set. And we use the training set to fit the model. And when we say things like fit the model, that just means finding our fitted coefficients, finding the intercept and the slope, or the, your W terms or your beta terms for linear regression, or, whatever weights you have in your model. We use that. And then after we fit the model to that training set, we take those estimated parameters, W hat, and we make predictions on the validation set that we kind of separated out at the beginning. And we have some kind of metric. Okay, we have a way to measure how well the model performs at making these predictions. Common choice is mean squared error. We just say, how good are our predictions? And we do this for the different models that we have, and we compare the metrics. And by comparing the metrics, we try to choose the best performing model. So we'll start off with a cross-validation method called leave one out cross-validation, okay? And this one, it's a simple idea, is you just leave one observation out. So your training data is going to be all of your available data except for one observation. You leave one of them out, okay? And that one observation that you left out serves as the validation set, okay? And then each data point in your available observed data will get a turn at being the validation point, okay? And so you'll have a total of kind of n training or validation sets. So I'm going to demonstrate this with a toy data set. Our toy data set just has 4 observations, okay? And I will demonstrate leave one out cross-validation with just 4 observations, and each one of those 4 observations will get a turn at being left out, okay? So my x values are 1, 2, 3, 4, and my t, the target values are 1, 3, 2, and 4. And if I fit the data, if I fit a linear model to all 4 data points, this is what it looks like, right? So here my observations are 1, 1, 2, 3, 3, 2, and 4, 4. And the best fitting linear model is, why can't I read? 0.5 plus 0.8x. This is the best fitting line if you fit the line to all 4 data points, okay? But the way leave one out cross-validation is going to work is we take one observation And I think for the first one, we're going to leave out observation number 4. So this one's going to go poof and disappear, okay? And so if you leave that 4th observation out, now you only have these 3 data points, okay? And then you're going to say, all right, let's fit a linear model. What if I ask, what is the best fitting line for these 3 data points, okay? And so if you only see these 3 data points, the best fitting line is this, y equals 1 plus 0.5x, okay? So according to this, if I plug in x equal to 4, the value I would predict is 3, okay? So I bring back in that observation that I left out, 4 comma 4. I bring that back in. This is our actual value. The predicted value is 3. The actual value is 4. And so I measure how far off is my prediction for the 1 observation I left out, okay? And so that distance is 1. I square it. My squared error is 1, okay? So that's my first observation, okay? And so I do this, and so just kind of to have the code keep track of this, I fit my model to the training data, which is just observations 1, 2, and 3. I make a prediction for the 1 point that I leave out, and I'm going to take a difference between the actual value and the predicted value, and I'm going to square that difference. Okay. Here's my 4 data points, and this time I'm going to leave this data point out. Okay, so each observation gets a turn at being left out. So this one is going to poof disappear, and then we're going to fit a line to the remaining 3 data points. Okay, and so the 3 remaining data points are these points 1, 2, and 4. And if you fit a line to these 3 points, the best fitting line is y equal to 0.5 plus whatever this is, 0.92857x. And then we bring it back that point that I left out, 3 comma 2. I put that back in and I say, okay, how far off is my prediction? Okay, so the actual value is 2. If we use this fitted line, it would predict a value of whatever this is, 3.28571. Okay, so I take that distance and I square that distance, and that square distance is going to be 1.6531. All right, and we just keep doing this, all right? We do this for every single data point. So again, here's all 4 of our data points. This time, this observation is going to be left out. So if I cover this observation up, and I just have these 3 observations left, 1, 3, and 4, and I say, okay, what is the best fitting line for these 3 data points? And when you do that, this is what it looks like. Y is negative 0.14286 plus this 0.92857x, all right? And then we say, okay, well, what do we predict if x equals 2? And the actual value is 3. And so this difference is 1.28571, and we square it 1.6531. You know, there's some symmetry here just because it's such a simple data set. And then finally, the 4th observation, or this observation, will be left out. Okay, so again, each observation is left out, and so now I'm fitting a line just to these 3 data points. And when I do that, I bring back in the point I left out right here, and I measure this distance and I square it, and that squared error is 1. Okay, so what we've seen is we've had our original data had 4 data points. Okay, and each time we leave one of them out. Each time we fit a line to the remaining 3 data points, and we make a prediction for the one that we left out. And then we measure how much error there is between the one we left out and our prediction for that one we left out. So we have a 1, we have a 1.6531, a 1.6531, and a 1 there, okay? And so if you add them all up, your total squared error is 5.306, and your mean squared error is going to be 1.3265. And so that is going to be your measure for how, our cross-validation, our leave one out cross-validation number for this toy data set. Okay, let me give you your first view quiz answer, which is the letter D. D as in dog. D as in dog. Okay. All right, there is a cross-validation function built into R in package boot. So you can use boot to do bootstrap, but also do cross-validation. And so you do this by fitting GLM, which is close, similar to a fitting an LM, at least its usage. And so I could say, hey, here's all of our data, which is our 4 data points. And I say, hey, fit a linear model, just T as predicted by X. That's going to be that. And then I can do leave one out cross-validation by doing cv.glm. I take all of our data. I also put in all of our linear model. And then it does the calculation. And then our mean squared error is stored in this delta vector. The first value in the delta vector is our mean squared error. And so we could see when we do use library boot in R, we get the same value, 1.326531, which is what we calculated manually when we drew all of our pictures and measured that difference and calculated the mean squared error ourselves. So that's always, I always think it's comforting when your manual process aligns with what R's package calculates. Okay. All right. So just a side note is generally you don't do cross-validation just for one model and then leave it at that. Okay. Cross-validation is used in the process of trying to compare different models for the data that you have. Okay. So when you use cross-validation to evaluate a model, you get just a single cross-validation score for that model. Usually the mean, just kind of your mean squared error. And in our case, we did, we had a toy data set with 4 data points. We performed leave one out cross-validation. We fit the linear model n times, and that produced n cross-validation values. And then we calculated the mean squared error there, okay? But again, you do this, you get one score for one model, in this case, our linear model. So again, just to kind of summarize, when we left out this point, we had a squared error of 1. When we left out this point, we had a squared error of 1.6531. When we left out this point, our squared error was that. When we left this one out, our squared error was that. And so on average, our mean squared error is 1.326, okay? And then usually what you do is, again, you don't do cross-validation by itself for just one model, is you try out another model, okay? And so you might have a quadratic model or a model that has a log transformation or something like that, right? So you try out a different model, and I said, maybe a log-log model or a polynomial model, right? You just have some other kind of thing, and you're saying, look, I fit a linear model, and this is what we got. If I fit a different model, what kind of cross-validation error would I get? Okay, and then for that other model, again, you fit it n times. You figure out your cross-validation score for that alternative model, and then you compare what was the cross-validation score for this one versus what's the cross-validation score for this one. And you have now a measure of how each model performs at predicting values that it hasn't seen, okay? Because cross-validation is explicitly done by training the model on certain values and then asking it to make predictions for new and unseen values. Okay, so the related thing that we have is k-fold cross-validation. This is probably the preferred method over leave one out cross-validation. And leave one out cross-validation, it's simple, but it has some big drawbacks, and that is, number one, it is computationally expensive, especially if you have a big data set, okay? Because if you have a big data set, remember, with leave one out cross-validation, each of your n observations gets a turn at being the validation point. So that means you have to fit your model to the data for observation 1. Then you repeat the process for observation 2. And so if you have like 1 million data sets, you got to fit the model 1 million times and make a prediction for each one of those things. So that's annoying, okay? And computationally expensive. And then the other thing is that basically every model that you fit is going to be almost exactly the same as the other models, okay? Like just ever so slightly different, because if you got 1 million data points, you're fitting a model to 999,999 points, okay? And then you fit it again to 999,999 data points, of which 999,998 of them are exactly the same. And basically, just one of them is different. And so if almost all of these data points are exactly the same, basically your two models are going to be like almost exactly the same, right? And so your resulting coefficient estimates end up being super highly correlated, and you run the risk of overfitting your training data. Okay, so an alternative is to use what we call k-fold cross-validation. And this takes our training data and it splits it into k approximately equal sized blocks. So you might do something like 4-fold cross-validation and you split it into 4 chunks, or 10-fold cross-validation and you split it into 10 chunks, where k is just some arbitrary integer, okay? And then each time you do it, one block serves as the validation set, and the remaining blocks combine to be the training data, okay? So here's just kind of an illustration of 4-fold cross-validation. We would run 4 iterations, and each of these things is what we call a fold of the data, okay? So we've split the data into 4 chunks, and during iteration 1, we use these 3 chunks to be our training data, and we validate it on this 1 chunk, okay? And then during iteration 2, we use these 3 chunks to be our training data, and this one's our validation set, and so on and so forth, okay? And so every observation gets an opportunity to be part of the validation set, okay? It's just, but now we only have, say, 4 folds or whatever we have, okay? And so in this example, our Olympic data set, we have 28 observations total, okay? And so I'm going to just kind of perform 4-fold cross-validation. And what that means is I'm going to split my data into 4 chunks of 7 observations each, okay? Randomized, okay? 7 random points. And for each iteration of k-fold cross-validation, I'm going to fit my model to 21 of the data points. I'm going to use 21 data points to estimate my slope and intercept and other coefficients. And then I use those resulting slope and intercept estimates to make a prediction for the 7 data points that I left out in my validation set. Okay, so here's all 28 data points, and just arbitrarily, okay, how do I do this? Okay, these, let's say these 7 will be the data points in my validation set, okay? So all 28 observations will get partitioned into 4 sets, and this is just one of the 4 sets. One of the 4 sets is these these 7 points in red, 1, 2, 3, 4, 5, 6, 7. This is one of the validation sets. This is validation set C. And we fit the data to the remaining 21 points, okay? And to kind of illustrate how this is going to work, we are going to fit a whole bunch of models, okay? So we divide the data into 4 random blocks. Each block will have a turn at serving as the validation set. And we're going to try fitting a linear model, a quadratic model, a cubic model, 4th order polynomial, 5th order, 8th order polynomial, and just for fun, a 17th order polynomial. Of course, it probably doesn't really make sense to do that, but we will. And then what we'll do is we'll calculate the total squared error for each model, for each validation set, okay? And we're going to find the cross-validation score by averaging the squared error for each model, okay? So I just kind of shuffle up my 28 data points. I split them into 4 sets, and I'm going to keep track of all of this. And basically, this is the code that I'm using to do cross-validation, okay? So the v index is going to be the index of my validation set. So let's say these are let's say it's observation, 15, or out of 28. Let's say it's observation 10, 13, 17. I don't know. You list off 7 data points, right? So those are going to be the ones that will be in my validation set. And so my training set will be, remember my x variable is year, and my t variable or the y variable is time. So I'm going to remove the validation index, those 7 values. And so I'm going to have 21 observations in train x and 21 observations in train t. And then my validation x and validation t will be the 7 that are part of my validation index. Okay, I fit my training data, or I create my data frames by having training data frame for the training x and training t, and validation x and validation t. So this has 21 observations, train has 21 observations, valid has 7 observations. I'm going to fit a linear model using just the training data, okay? I say predict t based on x. This is going to give me a slope and intercept. And using the slope and intercept that I found by using my training data, I say now make predictions, okay? I use that model 1's slope and intercept. Now make predictions for the 7 observations that I left out in the validation set, okay? And so these will be my predictions. And then I say, all right, now compare the actual values in the validation set with those predicted values. Take that difference, square them, add them up, and divide by n, okay? I do the same thing, but this time I'm going to fit a polynomial model. And so I'm going to say predict t using a 2nd order polynomial model, using only the training data. Now that you have that model, make predictions on the validation set to get your predictions, t hat 2, and then take the difference between the actual values and the predicted values, square those differences, add them up, divide by n, okay? And so this is how it goes. And then I just do the same thing. And basically I've just copied and pasted my code, but I said do it for a 3rd order, 4th order, 5th order, 8th order, and 17th order polynomial. I'm just copying and pasting the code, okay? And then I have the whole thing wrapped in a for loop, okay? And I say do this for the 1st validation set, then do it for the 2nd validation set, do it for the 3rd validation set, because I have my different sets listed off in this list here. Okay. All right, so this is, we're just going to take a look at one of these validation sets, this validation set of these 7 data points, and we'll see how this performs. So basically, I'm going to remove these 7 data points. Okay, so if you kind of stare at the thing, you'll see the 7 data points disappear, and we're going to fit a linear model to the 21 remaining data points. Okay, so if I remove those 7 data points, this is the 21 remaining data points. And here's the line, and this is now the line I fit. And then I bring those 7 data points back, and I say, how well did you predict those 7 data points that you left out? Okay, so again, here's the original data. We fit it to this, okay, original data, and then I say, now predict, using that blue line, that same blue line, predict those 7 points I left out, okay? Can you guys see that? All right, so, we measure this, and we say, okay, what is the mean squared error on this particular set of 7 data points? And we get 0.0319, okay? All right, we do the same thing. Here is all 28 points. Here's my 7 data points. We're going to throw those away, or hide them, I should say. And then we fit a quadratic model on the remaining 21 points. Okay, so I fit a quadratic model on the remaining 21 points. I bring back those 7 points. Okay, and I say, how well does it predict these 7 points? And when we do that, we get a mean squared error of 0.025. Okay, repeat. This time, we're going to fit a cubic model. So on the remaining 21 points, we fit a cubic model. This is what it looks like. We bring back those 7 points, and this is what we get. Okay. Here it is. We'll try the, fourth order. Okay, fourth order polynomial, and this is what we get. If you do it to the remaining 21 points, we bring back those 7 points. How well did it predict? This is what we get. Here it is, the entire data set. Do a fifth order polynomial, right? And so, as we increase, this one's the 8th order polynomial, okay? So as I increase the order of my polynomial, we get more flexibility, and we're able to fit some of these points, okay? And then now we measure again, how far off are we? So, all of our data, and this is what we have there, okay? And then I think this one's the 17th order polynomial, just for fun, okay? And so with the 17th order polynomial, and you say, hey, fit it to these 21 data points, because there's so much flexibility, it's able to fit some of these points like perfectly, okay? But this is not a line that, we would say we've overfit this data, right? We've overfit these 21 data points. And so when I bring back the original 7 data points, or not the original, but the 7 data points in my validation set, we see it does a terrible job at predicting this point, because, with the 17th order polynomial, it just kind of shoots off. And so now my mean squared error is this ridiculously large, 1,640. Running out of battery power here. Uh-oh. Let's buy some more batteries. Okay, so we're trying to fit it to, when we hide these 7 data points, we fit it to the remaining 21. We bring back those points, and we get, terrible error. And this was just for one. This was just for validation set C, okay? And, we would repeat this process with all of the different models, the linear model, quadratic, cubic, 4th order, 5th order, 8th order polynomial. We would repeat this process for each of the validation sets. We had 4 of them. Now, I didn't draw every single one of them, but that was just for validation set C. If I did it for validation set A or B or D, these are some of the different values that we get, okay? And so you can see these are the numbers that I had for validation set C. I had 0.0319, which was this one, 0.0319, and then for the quadratic, 0.025, and the cubic, 0.0131, okay? And this is what we have, 0.0319, 0.025, 0.0131, 0.0192, or whatever, okay? So we do this for all 4 validation sets. And then we take the average of these things. So, for the linear fit, my cross-validation score was 0.0224, 0.0258, 0.0319, and 0.1896. And when you average all 4 of these, you get 0.0674, and so on and so forth. Why do you think why do you think validation set D has a number so much higher than everything else? Right? Because you're looking at this 0.0253, 0.0371, 0.025, 0.1625. And then we have 0.046, 0.029, 0.0131, and then 0.14. And then 0.056, 0.0216, 0.0192, and 0.1669. Any suspicion as to why this one is so different?
Is it possible they just randomly chose the four different points to be a B?
Yeah. So if you look at the original data set, this one I would say is kind of an outlier, right? And so I think, so this observation ended up in validation set D. And so if you imagine fitting a linear model to this, right? Like let's say you leave this one out and you're fitting a linear model to everything else. Then when you measure the error on that one, it's going to just be like way bigger than everything else, okay? So like, I don't know. So that's what's going on with validation set D, okay? And then so when you have like the 8th order polynomial and stuff, it's actually able to, perhaps by coincidence, able to fit that one point pretty well, okay? And so anyway, you look at these cross-validation scores, and you get 0.0674, 0.0624, 0.0571, and so on and so forth. And the lowest one is the 8th order polynomial with 0.0419. Okay, so based on these results, it seems like the 8th order polynomial has the lowest cross-validation squared error. And the 3rd order polynomial, this one, has the second lowest. Okay, and so, you know, based on this, maybe we would pause to think about which one we would choose. You know, generally we just kind of go with the lowest cross-validation score, but you have to wonder, like, is the 8th order really that much better? And I would say we should use the 3rd order polynomial. And furthermore, to kind of test this out is one disadvantage of k-fold cross-validation is that you randomly split your data, right? So we took our 28 data points and we split them into 4 groups of 7. And so if someone else runs it, they're going to get a different 4 groups of 7, okay? And so they're going to get different validation sets, and they're going to calculate different kinds of things. And so here, if I rerun the exact same code, but I change my starting seed, you can see my cross-validation scores end up different, right? So the average, we're looking at this last column here, and we get 0.0674, 0.0624. With a different thing, we get slightly different values, 0.0632, 0.0559, 0.0464. And here we see the 8th order polynomial now no longer performs very well, okay? The 17th order polynomial also performs very terribly again, okay? And so the 3rd order polynomial has kind of performs the best here, and the 8th order polynomial performs, you know, second to worst, okay? And so k-fold cross-validation is subject to randomness, okay? And so here I run it a 3rd time just to kind of see how it goes. And this time, 3rd order polynomial does well, and then the 8th order polynomial is now second best, okay? And so depending on the seed, you can get different cross-validation results, okay? So we said k-fold cross-validation is a way to avoid computational expense of leave one out cross-validation, but generally you want to run your k-fold cross-validation more than once just to kind of see if you get results that agree, okay? Because every time you rerun your k-fold cross-validation, you're probably going to get slightly different results, and you're hoping for, you know, a set of results that that agree on a particular model and saying this one's the best. All right. Okay, let me give you your second view quiz answer, which is the letter E. E as in elephant. Okay. All right, and so So that's kind of how cross-validation works. We can do cross-validation again with library boot, and you can specify an argument k, which will tell you how many folds to do. If you leave the k argument blank, it does leave one out cross-validation, which we've seen it do, okay? And then the score is going to kind of provide your average scored error. So I'll run cv.glm a few times, and we'll see that there's kind of some randomization or randomness. So here I say do four-fold cross-validation. We're going to just fit a linear model. I have poly year order 1. I could just do time based on year. And so here with four-fold cross-validation, when I ask for the score, I get similar, but not exactly the same, right? 0.0643, 0.0659, 0.0576, okay? Here I do a quadratic, and I get different results, 0.062, 0.0469, 0.0648. Here it is with a third order fit, and I get different results here, okay? Whereas when you do leave one out cross-validation, okay, there is no variation, okay? When you do leave one out cross-validation, every single time you've got, in our set of 28 observations, it's going to be 27 observations, you leave one out. 27 observations, you leave one out. And all 28 observations gets an opportunity to be in the validation set. And so this leave one out cross-validation and follows the exact same process as this one. And so there's no randomness when you do leave one out cross-validation, okay? However, when you have k-fold cross-validation, when I run it here, I get 4 groups of 7, and so I get certain scores there. And here I run it again, and I get a different 4 groups of 7. So every time I run it, my folds are a little bit different, and therefore the results end up being slightly different, right? It's kind of just like, I don't know, imagine you have a classroom, and then you're in a classroom with the same students, but one day we randomize your groups and we have 4 teams, and then we have you guys play a game, and maybe team A wins, okay? But then we have the exact same students, and we randomize again, and we have another four teams. We have team A, B, C, and D this time instead of teams 1 through 4. And then because it's random, like the team that you end up on is a little bit different, and so maybe that's like a high performing team or lesser performing team, even though it's the same original or same set of students, because the way the teams get split up or because the way the folds get split up differently, you have different outcomes and things like that. So with these 4-fold cross validations, you get there's randomness at play. So that is one of the disadvantages of k-fold cross-validation, is that it is subject to randomness, and so we do recommend that you run k-fold cross-validation multiple times to make sure you find the best model there. Okay. All right. So the summary here. What did I do? And I copied part of this from Wikipedia. Cross-validation is a method to see how a particular model will generalize to new data. The goal of cross-validation is to test the model's ability to predict new data that wasn't used in estimating it in order to flag problems like overfitting. And then multiple rounds of cross-validation are performed using different partitions, and the validation results are combined or averaged over the rounds to give an estimate of the model's predictive performance. All right, so that's an important concept as far as machine learning and fitting models go. This is kind of the way we evaluate model performance. Okay, we no longer look at, are my assumptions violated or are they met? What is my the statistical significance of each of these predictors? Okay, we're moving away from that classical statistical approach and we're moving towards just how well are we making predictions, and we evaluate it using cross-validation. Okay, let me give you your final view quiz answer, which is the letter C. C as in cat, and we'll go ahead and end here. Yeah, so we'll see you guys on Wednesday. It's good to see you guys in person, and we'll see you in a couple days.